So in the last lecture, we started with understanding the iterative methods, right? So we saw that we start with some initial guess and then we generate a sequence of the iterates, which is expected to converge to the solution of the underlying problem, right? And we also saw various criteria to stop these iterative algorithms, like based on the absolute error, based on the relative error. So I'll just discuss few more general things regarding designing any of the algorithm. So, suppose we design some algorithm, right? So how do we determine that what is the quality of that algorithm, or it is going to be useful or not, right? So there are few factors which really determine the quality of any of the numerical algorithms. So first is the accuracy. What do we mean by accuracy of the algorithm? So whenever we design any numerical algorithm, it should be able to point out that what is the magnitude of the error which is expected when we are going to get, say, outcome of that algorithm, right? So for example, we saw the bisection method. So in the bisection method, we are able to reach till the desired tolerance. We set the tolerance, say, epsilon, and we are able to reach that desired algorithm, desired tolerance. But in further, as we progress with this course, we will see some other algorithms where we get the solution, and that like your algorithms would tell that, okay, at least it should give the some idea about the error, that okay, this is the error which is to be expected in the numerical solution. Okay, the second factor, which is an important factor, is the efficiency of the algorithm, whether the algorithm is efficient or not. What do we mean by the efficiency? Is that whenever you design some algorithm, it should terminate in a reasonable amount of time, right? So suppose you're designing some numerical algorithm and it has some great theoretical properties. You are able to prove theoretically that, okay, this has this property and multiple properties. But suppose you're going to implement those algorithms into the computer and it takes unreasonable amount of time to give the outcome, right? So then those algorithms are not going to be useful. So efficiency means that it should terminate in a reasonable amount of time. And third factor is the robustness. So the algorithm is robust, meaning that it should basically work under any weather conditions, meaning that suppose either algorithms would yield a correct result, okay, and if it is not able to give the correct result, it should terminate with some warning that that it has these limitations, or it is not able to produce the say the result because these conditions failed, right? So it should not produce an incorrect result. So either it should produce a correct result or it should terminate with some warning. Okay, so the robustness meaning that it should work with under, suppose you have some certain parameters, you vary those parameters, it should not change the behavior of the algorithm that, okay, under certain parameters it works and you change the value of the parameter, it doesn't work. So it should be robust in that sense. Okay, so we will relook into these notions in more detail when we will really see the implementation part. Okay, so there I will try to emphasize that while implementing, how do we take care of these things. So we also started with the methods of finding the roots of the nonlinear equations, right?
Yes, ma'am.
So there we already saw the bisection method. So bisection method, let's quickly review what do we do in the bisection method. So given the function fx, suppose this is a function fx, graph of the function fx. Okay, what we are interested in finding the approximation of the root, which is x star here. So how does this algorithm works? That you first choose an interval a b such that the f changes the sign in this interval, right? So basically we are going to bracket the root. So we are going to take the initial guess a and b such that fa into fv is strictly less than 0, right? That is the first step. And then we find the midpoint of this interval ab, which is going to be the approximation of the first approximation of this root x star. So x1 is going to be, so this is going to be approximation of x star. Okay, and then we check what happens to the fc. So based on the behavior of the fc, we determine what to do next. So if this fc is equal to 0, then we end the algorithm. If this is not equal to 0, then this will have a sign. So if it is greater than 0, so then in that case, we replace the interval to be AC, right? And if it is less than 0, we take the interval to be CB. And then we find the new midpoint, right? So we find C new as, so this is going to be my new interval, AB in either of the case. And then you find the new midpoint, A plus B by 2. And you can check the relative error. And if this error is less than tolerance, then you stop. So this is a prescribed tolerance. Then you stop. Otherwise, you repeat this algorithm. Right? So this is a basic idea of the bisection method, that each time you find the midpoint of the interval which brackets the root, and that is going to be the midpoint is nothing but the approximation of the root. And we saw that the error at the n plus 1th step is approximately half of the error at the nth step, right? That is, this algorithm converges linearly. Okay, and I pointed out that this is one of the drawback of this algorithm also, that when you go from one iteration to the another iteration, it is just the error is going to be approximately half, right? So in that sense, this algorithm is very slow. Okay, and I pointed out some other drawbacks also for this algorithm. But what we are going to see in today's lecture, and another algorithm which is called as the Newton's method. Or this is also called the Newton-Raphson method. And this algorithm tries to overcome the shortcoming which we have in bisection method. So what the important thing here is that we will see that this algorithm in Newton's method, it will converge with higher rate than what we bisection method. Okay. So what is the idea of the Newton's method? So let me try to explain it geometrically, and then we will try to write down the steps. So I have a function fx. So this is my function fx, and I know that this is my exact root. At least in this graph, I can see where my root lies, right? Okay, so again, this is going to be an iterative method. So this means that I will start with some initial guess. So here my initial guess is x. I'm going to call it as x naught. Okay, and this initial guess I'm going to choose sufficiently close to the x star. Suppose this is my initial guess x naught. Okay, so in this method, what do? We consider the approximation of this fx. So let's consider this point x naught, f at x naught. So assuming that this x naught is sufficiently close to x star, what I'm going to consider? I'm going to consider that my fx can be approximated by the tangent line at this point, at x naught, fx naught. Okay, that is, I'm having the graph fx and I start with the initial point x naught and I consider the tangent line x at the point x naught, fx naught, and I take that as an approximation of my fx. Okay, so meaning that if my x naught is very close to x star, the tangent line will be very close to the function fx in the neighborhood of x star. Okay, then what will be the approximation of my root? So the root of this line, let me write the x star here. So this is my x star, and this is going to be the first approximation of this x star. So this is my x1. Okay, so you take this tangent line and the x-intercept of this tangent line, meaning the root of this line is going to be the approximation of my x, right? Next, what I will do, I will take x1 fx1 as my next iterate. Okay, and I consider the tangent line at this point. Okay, so this is a little mess here, but I think you can understand that I'm going to take the tangent line at the x1 fx1, and wherever it intersects with the x-axis, that is the root of this line, is going to be my next approximation of the x star. That is my next iterate. Okay, so this is how I'm going to generate the sequence of the iterate. So now let's try to explicitly write down what is going to be my x1, x2, and like that. So what we are doing, so we take x naught to be the initial approximation of the root of fx is equal to 0. Okay, and let's consider the tangent line. At this point, x naught, fx naught. And let's say it meets the x-axis as x1, right? So this is my approximation of the x star. So what is going to be the exact form of the x1? So basically you can see what is the equation of this tangent line. So it is passing through x naught, fx naught.
X minus x naught.
Y minus y naught equal to dy by dx x minus x naught.
Right, so you will be able to write it explicitly. So it is going to be fx naught plus, so I'm using this slope at x naught by f prime of the x naught into x minus x naught. So this is going to be y at x, right? And what I want x1. So basically at x1, we know that the y is 0, right? So what I'm going to have, I will have that fx naught plus f prime at x naught at x1 times x1 minus 0, right? Because basically you can see that this is a point x1 comma 0 and this is the point x naught comma fx naught. So you can see the slope basically here is going to be f prime of the x naught. So what do we get from here? This is going to give us that x1 is x naught minus fx naught divided by f prime of x naught. Okay. So of course you have to keep in mind that I'm assuming that, so I will formalize all these assumptions when I will state the convergence result. But since we are going to have f prime of the x naught in the denominator, we will have that this is not equal to 0, right? Likewise, for the other iterations, we will have that f prime of the xi is not equal to 0 for all I. Okay, but we will formalize these assumptions in the convergence result. So this is my next iterate. Now what I will do, I will take this as a next iterate. And assume that the tangent line to the curve y is equal to fx at this point x1 fx1, this meet the x-axis at x2. Okay, so then as in the previous case, we will be able to find that x2 is nothing but x1 minus fx1 divided by f prime of the x1. Okay, and if you continue this process, what I'm going to get, my n plus 1th iterate xn plus 1 is going to be xn minus fxn divided by f prime of xn. Okay, so this is known as the, so this iterative method is known as the Newton's method. So we can formalize the, write down it in the form of the algorithm. So here, as you can see, that I'm requiring the derivative of the function f, right? I'm going to assume f to be a differentiable function, at least for this algorithm to make sense. So what is going to be the first step? Okay, so we have to compute the f prime also. And then you're going to start with the initial guess. X naught, and for k is equal to 0, 1, 2, 3 up to the, we will set a stopping criteria. So up to that step, you can compute the iterates by using this formula. And you're going to repeat it. So you can find the error also. Say I'm computing the relative error. So you can repeat this step until so you can set the tolerance. So until your error is less than the set tolerance. Okay. So this is, I'm writing in the form of the steps so that, in case we are going to implement it, so you know that how the things has to be done. Okay. And one more difference you can spot out here from the bisection method, that in the bisection method, we needed to bracket the root. That is, we were starting with the two initial guess, right? A and B, basically we were starting with an interval, the 2 points A and B. But here we just starts with the one initial guess, which is X naught, and then that generates the algorithm. Okay, so now let's take one example and try to see how this algorithm really works. So I'm going to find out only 3 iterations, starting with initial guess X not equal to 1. So you have to perform 3 iterations. To find the so 3 iterations of Newton-Raphson method. So I'm going to use the NR shortened notation for the Newton-Raphson method. Okay, so let me write here. So I will use NR method in short. So we are going to find the root of this nonlinear equation fx is equal to x minus exponential of minus x, this equals to 0. Okay, so it's a direct question. You have been given x naught is equal to 1, and so we can simply compute the derivative of fx. So fx is given to be x minus exponential of minus x, and we know that this is a differentiable function. So its derivative is 1 plus exponential of minus x. So you can find the first iterate, which is going to be x naught minus fx naught divided by f prime of x naught. So you can simplify this because you already know x naught equal to 1. So this is going to give us 0.999. And likewise, you can compute x2 is equal to x1 minus fx1 divided by f prime of x1, and x3 is going to be x2 minus fx2 divided by f prime of the x2. So you can find their approximate value, because once you know x1, you will be able to compute x2 and likewise x3. So this is how this algorithm works. So it's quite simple, right? So I'll give you one exercise here. So you have to find the iterative formula using the Newton-Raphson method to compute the reciprocal of a natural number, say n. Okay. So just try to see what exactly is being asked and try to write it down. Is the question clear? And is the algorithm clear?
Yes, ma'am. Yes, ma'am.
Okay. So
मैम NR मेथड ये फंक्शन डिक्रीजिंग के लिए या सभी के लिए हो सकता है?
this method?
Yes, ma'am.
So there's the
NR method.
Yeah, so this Newton-Raphson method, I have not stated any condition on the function fx other than that I need the differentiability of the function f. Further condition, whatever I require, for the error, the convergence of this sequence, I will state in the next theorem. But as if to make sense of this method, you don't need anything other than the differentiability of the function f and the conditions that the f prime should not vanish at the any of these iterates. Okay, because in that case you can see that you are not. Okay, so these are the only things you require to make sense of this algorithm. Now what I will require for the convergence of this algorithm, I will state further in the next theorem as I'm going to discuss the error analysis part. Okay, so coming on to that question of the convergence. So the main reason to start with this new method was to see whether we can have a better convergence than the bisection method, right? To get there, we were having a linear convergence. So when we are designing any new method, we expect a better convergence than the existing method, right? So we are going to see that in this method converges with the quadratic rate. That is, it has a quadratic order of convergence. So for that, we have to see the convergence analysis. So I'm going to state this as a theorem. So now you will see what all assumptions I'm going to put on the function f to have the convergence of this iterative sequence. So I'm going to assume fx, f prime x, and f double prime x. They are continuous functions for all x in some neighborhood of the exact solution, which let me call it as exact root, which is a x star. And of course, x star is the root, so I have that f at x star, this is equal to 0. And also what I need is that the f prime should not vanish at the x star. Then, if my initial guess is chosen sufficiently close to x star, then this sequence of iterates, which we call it xn. So let's give it equation number. Series is given by 1. This will converge to the actual root, and moreover we will be able to obtain that if I consider the error in the n+1th iterate divided by the error in the nth iterate, square of that, the limit is going to be f double prime x star divided by twice of the f prime of the x star. Okay, so what can you conclude by this say equation 2? Can you say something about the order of convergence? So you can observe that this is a constant here, right? So for the large value of the n, what will happen? Your xn plus 1 minus x star is approximately constant times xn minus x star square, right? So this means that this method is going to converge with have a quadratic convergence, right? So let's try to prove this theorem. But I need to recall, I mean, you all already might be knowing the Taylor's expansion. but I need to recall that because I'm going to use that to prove this theorem. So this is just recalling of the Taylor's theorem. So let's give it a theorem number. So what does the Taylor's theorem say? Can any of you tell me? So if I have information about the differentiability of the function fx, that fx has n plus 1 continuous derivatives on the interval ab. So here for some n greater than or equal to 0, and if we take x naught to be any point in this interval ab and x naught 2 points in this interval ab, then you have the following expansion of f in the neighborhood of x naught, right? So you can write this as fx naught plus x minus x naught f prime of x naught. Sorry. And the second last term is going to be x minus x naught raised to power n divided by factorial n. Nth derivative of f evaluated at x naught. And the last term, which we call the remainder term or the error term, this is going to be fn plus 1 evaluation of the n plus 1th derivative of f at some xi, where this xi lies between x naught and x, right?
Yes, ma'am.
So you have another form of this term. So the remainder term can be written as in this form also. Actually, when you're going to prove this theorem, you're going to get it in this form, and then you have to see how do you get this term. So this is for something for you to think about, that what does it, there's a one theorem which we apply to get from this step to this term. Okay, so you think about it, that what we have to do to get from this integral to this exact term. Okay, so we are going to use this theorem to prove this convergence result, which is stated in theorem 1. So let's go back to the proof. So we have been given the information about the second up to the second derivative of the function f, right? So I'm going to use the Taylor's theorem to have the expansion of f in the neighborhood of the xn, okay, where xn's are the iterates. So we are going to get fx as f of xn plus x minus xn f prime of xn plus x minus xn square divided by 2 f double prime at some xi. So this xi will lie between x and xn, right? This is for any x. So I will formalize the thing as we proceed further, but here I've just written what I have from the Taylor's theorem. Okay. Now in particular, I'm going to take x is equal to the actual root, which is x star. Okay, so if I consider the expansion of f in the neighborhood of the xn, I will get f of xn plus x minus x star minus xn, f prime of xn plus x star minus xn square divided by 2 f double prime of. So note that when you will apply this Taylor's theorem by expanding fx star in the neighborhood of the fx1, you will get one xi, right? Likewise, for each of the xn, you will get a different xi, right? So I'm going to call it as a xi n. So where xi n lies between xn and x star. Okay, now we know that my x star is the actual root, that is, this is equal to 0. So from here, what I can find, so I'm going to solve for x star from here. So I will get my x star as xn minus fxn divided by f prime of xn minus x star minus xn square divided by 2 f double prime of xi n divided by f prime of xn. Okay, so I have this. So from here I can see what is going to be. So this is what, using the Newton-Raphson method,
xn plus 1.
so this is xn plus 1. So what do I have? I have x star minus xn plus 1. This is nothing but minus x star minus xn square by 2 f double prime of xi n divided by f prime of xn. Okay, so let's give it an equation number. So this is 2, this is, let me give it a 3. Okay. Okay, so let me simplify one more step and then give the equation number. All right, doesn't matter. I can give it here itself. Okay, so from here we can observe that what do we have is that x star minus xn plus 1 divided by x star minus xn square. This is f double prime of the xi n divided by 2 f prime of the xn. So what I can do, I have a negative sign here, right? So I will change it to xn plus 1 minus x star. And here it will not make a difference because we have a square sitting here. So I will make it as xn plus 1 minus x star, and this is going to be xn minus x star. Okay. Okay, so we got some information, but I just exploited that we have the continuity of the function fx up to the second derivative, and using that we have got this. Right now, first of all, now let's try to show that the sequence xn, which we have got using the Newton-Raphson method, that will converge to x star. Okay, and then we'll try to obtain this relation 2. So now we are aiming to show that xn converges to x star. Okay, so and one more thing here, you have to observe that in the theorem, I just had this requirement that f prime of the x star is not equal to 0, right? But here I'm using that dividing by the f prime of the xn, right? So I have to have some way to have it that these f prime of the xn's are also not equal to 0. So that will just be justified as I will state that where my xn are going to belong. Okay. So let's first prove that this xn is going to converge to x star. So what is given to us? That f prime x, this is continuous. And secondly, the f prime at x star, this is not equal to 0. Right? So what can we say about the f prime of the x in the neighborhood of the x star? You have a continuous function which is not 0. Sorry?
It's not zero. It's not zero in the neighborhood of x star.
Exactly. So you will be able to find a neighborhood around x star where f prime x will not be equal to 0. Right? So we can choose a sufficiently, or we will find a sufficiently small interval. Let's call it x star minus epsilon and x star plus epsilon. And let's call this interval to be I, on which f prime of x is not equal to 0. Okay. So now I'm just going to introduce one quantity here. So which is, I'm just taking the motivation from this quantity because I will use it further. So I'm taking the maximum of f double prime of the x over this interval I. Okay. And I'm taking the minimum of f prime of the x over the interval I. And I'm going to call this quantity as m. Okay. So now what do we have from this equation? From 3, what can we say? So we can say that if I just consider the first iterate, so I can say that x star minus x1, this is less than equal to, so I'm just taking m to be the supremum of this factor. Basically, this will be less than equal to the this complete quantity will be less than equal to m, right?
Yes, ma'am.
So I can say that x star minus x1 is less than equal to m times x star minus x0 square, right? And if I multiply both sides by x star by m, what do I have? I have this m times x star minus x0 whole square. Okay. So note that I have not really told that how I'm going to choose my x0 so far, right? I have started, I know that there exists one interval where f prime x is not equal to 0. And now I'm going to tell you that how I'm going to choose my x0. So first of all, I will choose my x0 in the same interval I. Choose x0 such that x star minus x0, because anyways I'm working in that interval only, so my x0 is going to be in that interval. Secondly, I'm going to require that my x0 has to be such that m times of x star minus x0, this is strictly less than 1. Okay, then what will happen? So then from this relation, I can say that m times x star minus x1, this is also strictly less than 1. Is that okay? Because this quantity is strictly less than 1, right? So its square is also going to be strictly less than 1. So m times x star minus x1, this is strictly less than 1. That is the first conclusion I have it. And secondly, I can also have, so since we know that this quantity is strictly less than 1, so what can we say that if I take this quantity x star minus x naught square and x star minus x naught. So which one will be bigger and which one will be smaller?
And square one will be smaller.
So this is going to be smaller than this
Scale
quantity,
is small.
right? So from this relation, what do we have? We have that m times x star minus x1. This is less than equal to m times x star minus x naught. So m cancels out. So what do we have is that x star minus x1 is less than equal to x star minus x naught, and we know that this is less than equal to epsilon. Okay, so what does this imply? That I started with my x naught is an I, but my x1 is also belonging to the I. Okay, and you can apply this argument inductively. That is for, we have got it for x1. Now you apply it for the x2, x3 up to xn. So you can get it as so what I will get, the first information I will get that my xn is going to lie in I, that is x star minus xn, this is going to be less than equal to epsilon. And second information I'm going to get is that m times x star minus xn, this is going to be strictly less than 1 for all n. Okay, so one conclusion we have from here, that we started with x naught is an I, and we have the complete sequence xn that is also going to belong to I. Okay, so this is one conclusion. But what we are interested in the convergence part, whether the sequence xn converges to the x star or not. So for that, let's again go back to the relation of xn plus 1 and xn. So we have again from, what is the equation we have? 3. We have that x star minus xn plus 1. This is less than equal to m times x star minus xn square. Okay. And if I multiply m both sides, I will have this step. Okay. So now you apply the same thing to this term. So we know that m times x star minus xn, this is going to be less than equal to m times x star minus xn minus 1 square, and then you have a square of that. Right? And you can continue this process. So what I can say, I can say that m times x star minus xn, let me not write for xn plus 1, rather write it for xn itself. So I will continue this up to I reach x naught. Okay, so till that point I will continue. So what I will get? I will get this as m times x star minus x naught whole raised to power. What will be the power? 2 raised to power n.
2 to the power n.
Right? So you all are agreeing with that? Okay, so what do we got? What have we got is this. This is less than equal to 1 by m times x star minus x naught raised to power 2 raised to power n. And what do we know about this quantity? We know that m times x star minus x naught, this is strictly less than 1. Right? So does this conclude the result? What will happen as n tends to infinity?
xn tends to x star.
So when n tends to infinity, this term will go to 0. So what do we have is that xn will go to x star as n goes to infinity. So that is, we have the convergence of this iterative sequence to the actual root x star. Okay. So the convergence part is okay. So we got that if we start with a suitable x naught, then we will get a complete sequence. Suitable x naught meaning it is in the neighborhood of the x star. Then we will get a complete sequence which will lie in that neighborhood. And in that neighborhood, we know that f prime of x is not equal to 0. So that ensures that f prime of the xn is also not equal to 0. Okay, so I don't have to put it as a separate assumption. So by having each of the xn in this interval, I already know that f prime of the xn is not equal to 0. Okay, so it suffices to just have that f prime of x star is not equal to 0. Okay, so this is about the convergence. Now let's talk about that how do we get this relation 2. So this is also evident. So if you try to see the so this equation that is from 3. So we have that xn plus 1 minus x star divided by xn minus x star. This is equal to f double prime of the giant divided by 2 f prime of the xn. And if you take a limit both sides, so we know that xn converges to x and f prime is a continuous function. So f prime of xn will converge to f prime of the x. But what happened to the term f double prime of the giant? So what is the giant here? Giant lies between xn and x star, right? So we know that xn converges to x star, right? So and giant is lying between xn and x star. So what can we say about the sequence giant?
Giant tends to x star.
Right? So this sequence will also converge to x star. Okay, so like you can see that here we are using many things from the basic analysis, right? So if you have a sequence xn converges to x star and you get another sequence which is sandwiched between xn and x star, that will also converge to the same, that will have the same limit, right? So and we know that f double prime is a continuous function. So this will imply, so therefore what do we have is that limit of this factor is nothing but f double prime of x star divided by two f prime of x star. Okay, so this completes the proof of this theorem. And this also tells you that what are the requirements you have to have for this Newton-Raphson method to converge, right? So a few important things you notice here, that it is important that how you choose your x naught. Okay, so x naught has to be in the, it has to be sufficiently close to x star, that it has to lie in a small neighborhood around x star, right? And in the proof, we have seen that how the x naught has to be chosen. So note that we had this condition, right? So m is, so once you have the information about the function f, you will be able to find m. Okay, once you have m, this basically tells you that you can choose your x naught such that x star minus x naught should be strictly less than 1 by m. Okay, so theoretically, this also gives you the idea that how your x naught has to be chosen. Okay, so in case if your m is very large, you can see that your x naught has to be very close to the x star for this algorithm to converge. All right. And also, I can give this as a remark. Okay, first remark is about the how do we choose the x naught. So that I'm mentioning the same thing. So in order to have convergence of xn to x star, we should have my x naught such that x star minus x naught should be strictly less than 1 by m. Okay. And second conclusion which I can draw from there is that the Newton-Raphson method has quadratic convergence. Right? So if you compare with the bisection method, so in the quadratic convergence, meaning that when you go from one iteration to the another iteration, your error will be reduced by the factor 1 by 4, right? Okay, so is everything okay so far?
Yes, ma'am.
Yes,
All
ma'am.
right. Yeah, so we have seen that, okay, this is a nice method. And one more important thing is that if you're able to get hold on the correct x naught, okay, then this method will converge very fast, because you can see that the convergence, you're having quadratic convergence. So in compared to the bisection method, this is going to converge very fast, meaning if you set a given like for a given tolerance, you will be able to reach till that tolerance in a very few number of iterations as compared to the bisection method. Okay, but of course, so this is one of the major advantages of this method. So let me just list it out. So the advantage is so when this Newton-Raphson method converges, it converges quite rapidly. So which is an advantage over the bisection method. But at the same time, this algorithm also comes with a set of drawbacks. So let's discuss a few of them. So the first drawback is that it might happen that this method does not even converge in some cases. Okay, what are some cases that if you're not able to get hold on the correct x naught, then this method will not converge. Okay, so this is very sensitive to the initial guess. So the first disadvantage is that this method need not converge. And the instance where it might not converge, so one main reason is that you're not able to choose the correct initial guess. So it depends on how you choose the initial guess. So basically you have to have a good choice of the initial guess x naught. So let's try to understand this by taking one example. So let's take this function x is equal to 10x or x minus 10x equals 0. So if you apply the Newton-Raphson method to this function, and let me take two different choices of the x naught. So I'm going to start with x naught is equal to 4 and x naught is equal to 4.6. So I've already computed some of the values, so I will just list them out. So if you start with the x naught is equal to 4 as an initial guess, and if you compute x1 using the Newton-Raphson method, you will get this as 6.12016. Okay, the next iterate is going to be 238.40. The next iterate is going to be, so x1, x2, x3. So 1597.26. Okay, you can just verify it. Okay, but if I start with 4.6, I will get x1 as 4.5458, x2 as 4. 5062, x3 as 4.4942, like that. Okay, so you can see if you just go further and further, this sequence will not, so you can see you can find the approximate root, exact root of x equal to 10x, right? You just plot the graph of the 10x and you plot y is equal to x. The intersection will be the root of x is equal to 10x. And that you can see that it will this sequence is going to converge to the exact root, but this sequence is not converging to the actual root. So in fact, this is diverging, as you can see. Okay, so this method is very sensitive to the choice of the initial guess. And the second drawback of this method, not exactly the drawback, but if you see as a computational point of view, of course, it's a drawback that you have to compute the f derivative of the f. So imagine if your f is having a very complex nature, it's a very complex expression, and then you have to compute the f derivative of f. So numerical point of view, the computing the derivative of a function might be very expensive. Okay, so when we talk about the computational like time you require, that might increase because of computation of the derivatives at each step. So you have to compute the derivative and then you have to evaluate it at each of the iterative points, right? So this, in terms of the computational efficiency, this might be a drawback. So another source of difficulty is the necessity of having the. So let me write necessity of knowing f prime x explicitly. Okay, so in this context, let me take one example and see, you also need, so when we say that knowing f prime of the x explicitly, you also need the information about the, like the function has to be differentiable also, right? So you have seen the requirement in the convergence proof that we need the function has to be differentiable and also that it has to be twice differentiable, not just differentiable. So if I consider this function, so let me take fx is equal to x raised to power 1 by 3. And you just apply the Newton-Raphson method to this. So what is the relation I will get after applying the Newton-Raphson method is this. Xn plus 1 is equal to minus 2xn. Okay, so what will happen? If you start with the, say, x0 is equal to 1, what is the next iteration you are going to get? x1 is going to be minus 2, x2 is going to be minus, so this is going to be 4, x3 is going to be minus 8. So you will get a sequence of the iterates which is not going to converge to 0 because 0 is one of is the root of this fx, right? So if your function itself is not differentiable at the x star, then of course you cannot apply this method, right? And third drawback is again related to the choice of the initial guess. So I'll just explain it using a graph. So suppose so I'll just draw two lines. So I want a function, so let me draw it. Okay, so here, suppose this is my function fx. Okay, and I choose my initial guess to be say 0. So what will happen? Then I will take so this is my suppose x0. So I will take this my the tangent line at this point. So of course I have not drawn the graph correctly. So this has crossed it. So it should be so say let me just forget about this part. Okay, so I have to draw it. So let me just see how can I draw this. Okay, so I want this. Okay, so basically I just want to have this as a point of reflection. Okay, so of course I'm not able to draw the great picture here. So this will go further and coincide with this will give you the root. Okay, so basically I want to have this as a point of reflection. So what will happen if you will take this as an initial guess? Okay, let's start with this as an initial guess. Suppose this I take my x naught. Okay, so I'm going to take x naught f x naught, the tangent line on that, and that will say cut the x-axis at x equal to 0, and this is going to be my new root, right? The approximation of the root, and then I will take a tangent line at this to get the next retreat. But if you see from the given picture, you'll take a tangent line here, it will again come back to 1, right? So this is going to be, the algorithm is going to go into the infinite loop. So what I'm trying to explain here is that, so it might occur so the iteration sequence might repeat, which will result in an infinite loop. So this is in the sense that, so when can it occur? So if you take when you take a tangent to the curve fx, say at x is equal to xk plus 1, and it cuts the x-axis again at x is equal to xk. So you are taking a tangent at xk, and it is tangent line, and it is coming, it is cutting the x-axis at xk plus 1. But if you take a tangent line again at xk plus 1, it is going back to the xk. So then this sequence will get repeated, because when you will take a tangent line at xk, it will give you the xk plus 1, and when you will take a tangent line at xk plus 1, it will give you xk. So this is going to go into the infinite loop. Okay, so in such situation also, if you just start ending up choosing your x naught in such a way that it goes into this setting, then of course you will end up having an infinite loop. Okay, you will never be able to converge to the actual root of the function. And another instant may happen is, so let me again try to draw one picture and try to explain it. So suppose my function is something like this. So let me take a simple function. Okay, so if I choose my, so this I know that this is my root here, so I have a roots here. So if I choose my x naught in such a way that if my f prime at x naught is very close to 0, so we have this assumption that f prime of xi should not vanish. But suppose if I end up choosing my x naught in such a way that f prime of x naught is very small, it's not 0, but it's close to 0, then what will happen if you, so for example, f prime of x naught is equal to 0, meaning the line is parallel to the x-axis. So I'm just taking in the nearby to that point. So this will be, I will take a tangent line here, and you will see that the roots, so you started with this point, but the next root is going to be very far away from the actual root. Okay, so you should come near to this as you go to the next iterate. But what is happening, if you start this as your x naught, this is going to be your x1. Okay, so if your f prime of the x naught is very small, then also this algorithm will take a lot of iterations to converge, because initially it will just send the iterations far and far away from the the actual root. Okay, so it all boils down that how you choose your initial guess, and that will really determine that whether your iterations are going to converge or they are going to diverge. Okay, so coming on to the computational point of view, there's as I mentioned here, this has this drawback that you have to compute the f prime of the x explicitly to really use this iterative method, right? So which might get very computationally expensive if your fx has a very complex expression. So next remedy is that I'm going to propose another numerical method, which you will see will overcome this difficulty. Okay, I will not require to compute f prime of the x, but at the same time, I expect that that method should also have a better convergence than the bisection method, because that was the whole reason to go to another method, right? So that method is the secant method. So rest all the disadvantages which I shared, that is related to the initial guess. Okay, so initial guess has to be good. If your initial guess is good, the rest all things will not occur. But this part, that is computation of the derivatives of the f, you cannot avoid. Okay, so the next method which we are going to see is that there I will see that we do not require to compute the derivative of the f. We can just work with the the f itself and get a better convergence than the bisection method. So this method is a secant method, and I will try to explain it geometrically that what is the underlying idea behind this method. So it is very similar to the Newton's method, but of course we have to somehow get away with the derivative of the f in the expression, right? So, so let's take a function fx. Suppose this is a function fx. The graph of the function y is equal to fx. So in the Newton-Raphson method, what we were doing? So we took an initial guess. Let's take an initial guess x naught, and then we just consider the tangent line at x naught fx naught, and that we considered as an approximation of the function f, and we took the root of that line, right? Here instead, what I'm going to do, I will start with two roots, two initial guesses, say x naught, and let me take another initial guess, x1. Okay, and then I'll consider the points x naught, fx naught, and x1, fx1. Okay, and I'll take a secant line passing through this point, and this I will treat as an approximation of the function fx. Okay, so the root of this line, which is going to be this point, is going to be the approximation of the x star. So this is going to be I have already taken x naught x1, so this is going to be x2. So now next what I will consider the point x2 fx2, and I already have the x1 fx1, and I'll take a secant line passing through these 2 points. And the root of this tangent, the secant line, is going to be my next iterate. So this is going to be x3. Okay, so this is how I'm going to generate the sequence of the iterates, and we will write the final expression of that. So you can think about it, that what will be the, knowing x0 and x1 as I've explained here. Okay, let me write down. You can verify that. So we have to compute x2, right? We already know x0 and x1. So knowing x0 fx0 and x1 fx1, we can compute x2 by just comparing the slope of two lines. Okay, so I'm going to take the fx1 minus fx0 divided by x1 minus x0. And then I'm going to take the next 2 pointers.
x2,
x2 and the x. So I will take this as fx1 minus the evaluation of the function at x2 is 0 and x1 minus x2. So from here I can solve for x2. So this will give me x2 is equal to x1 minus fx1, and the factor which I'm going to get here is that x1 minus x0 divided by fx1 minus fx0. Okay, and if you simplify this, this is nothing but x0 fx1 minus x1 fx0 divided by fx1 minus fx0. Okay, and I will repeat this process. Now you will use using x1 and x2, we will get x3 as x2 minus fx2, x2 minus x1 divided by fx2 minus fx1, right? So likewise, if you continue, you will be able to write the general method, okay, which is given by. So let's write down the the general step. So we have xn plus 1, this equals xn minus fxn times xn minus 1 divided by fxn minus 1. Okay, so this method is known as the secant method, and you can see the name is evident from that we are taking approximation of the fx by a secant line. So that's why the name is secant method. So we'll try to see that what is a order by which this method converges, and whether in what sense it is better than the Newton's method. And of course, it is going to be better than the bisection method, because it is going to converge with a better order than the bisection. So these things we will see in the next lecture. So if you have any questions, you can ask now.
N greater than or equal to 0, ma'am, and we take n equal to 0 and x minus 1.
Sorry, so it should be 1.
1.
Thank you. Okay, so we stop here. If you have any questions, you can ask now.
Ma'am, which book we are following for this topic?
So most